In this class, I'm going to continue and expand on our discussion of the quantum mechanics of Coulomb potentials and spherically symmetric potentials, and in particular, the specific case of the hydrogen atom. Our discussion is going to focus this time around on our understanding of what angular momentum is and the ramifications that it has in experimental observations. And we're going to find that angular momentum is very useful and explains a lot of the properties of atoms, but that we actually need to include a quantum mechanical quantity that's associated directly with the electron, which is the spin of the electron. And we'll discuss the experiments that are related to these observations of angular momentum and spin. That is the Zeeman effect, which is a spectroscopic measurement, and fine structure, which is a spectroscopic measurement, and the Stern-Gerlach experiment, which comes from shooting atoms through magnetic fields. And then incorporated into this, I'll introduce some of the language of spectroscopic notation. First, we couldn't really spend enough time on it last round. I'd like to take a moment to remind you of the coordinate system that we're using in order to do our calculations. The Cartesian coordinate system is the one that you have known best over several years now, with x, y, and z axes at right angles to one another, forming a right-handed system. That is, x cross y gives you z, y cross z gives you x, and so on. Okay, and when we have a spherically symmetric potential, it makes a lot more sense for us to use spherical coordinates, where r is the distance of a point from the origin, theta is the angle with respect to the z-axis, and phi is the angle with respect to the x-axis. Phi is frequently called the azimuthal angle and would involve taking this vector and rotating around through 2 pi until you come back. Theta runs from 0 to pi. The conversions for the coordinates are here, and we have been using throughout our earlier lectures the the Laplacian and spherical coordinates, so I've just put it down here in order to remind you of that. Little reminder of what we talked about last time around. That if we start with the Schrodinger equation with a spherical potential and assume that the solution can be expressed as a product, then we can separate our variables, and the first variable to be separated out is the azimuthal angle, the function, the wave function as a function of azimuthal angle. And we find that that leads to quantization, where the wave function as a function of phi azimuthal angle, actually I take that back, as a function of the angle from the z-axis. I've been misusing the word azimuthal on this page. As a function of the angle from the z-axis, it results in a wave function that's got a quantum number where m sub l must be an integer. There will be other limitations on m sub l that come about. We stated last time around, and that's all that I'll do this time around, that the solutions to the theta portion, that is the azimuthal portion, of the wave function are called associated Legendre polynomials, and they are related to the Legendre polynomials, which are the solution to the equation for m sub l equal to 0, related to the Legendre polynomials in this way. And here are the first few associated Legendre polynomials, where x in this case well, these are the solutions to this equation, but for the purposes of our quantum mechanical solution, x is cosine of theta. That's why it's a function of theta. So writing out the full angular solutions, we talked about this last class, but this is a reminder. The result is called the spherical harmonic. Spherical harmonics are these functions as a function of L and M. These are the associated Legendre polynomials. I've got e to the I m here, all right, phi. And so the spherical harmonics are functions of both theta and phi. And the first few spherical harmonics are written out here. And the spherical harmonics plotted as a function on a polar plot as a function of angle from the z-axis are shown here. Now this begins to get into new material, so all of that was review from our previous class, but maybe, I hope, stated a little bit more succinctly. Now I want to talk about quantum angular momentum. And we'll start out in perhaps our typical way here, which is to start with an analogy to classical physics, where the angular momentum of a particle about the origin is defined, so angular momentum is L, is defined as distance from the origin crossed into the momentum, linear momentum of the particle. And this is a cross product. So just writing it out term by term, L sub x, then, the angular momentum along the x-axis, is the coordinate y, the distance in y. P sub z, momentum, linear momentum in the z direction, minus z py, and so on. Okay, those are the components Lx, Ly, and Lz. Now that we have a classical expression here, what we can do is rewrite each of these terms, Lx, Ly, and Lz, in terms of operators. So we'll start out with the Cartesian operators, and we make the substitution that the momentum in the z direction is h bar over I, partial of the wave function with respect to z, and momentum in the y direction is the partial with respect to y, and x partial with respect to x. So we can write out each of these Cartesian components of the angular momentum as an operator. When this operates on the wave function, then we get the angular momentum in the x direction. And because we have been working in spherical coordinates, we will now make the substitution of changing every one of these terms into spherical coordinates. And you can do that given the information that I've given to you on the previous page with respect to the definitions of the coordinates. When we do that, we find out that the operator for angular momentum along the z-axis, right, the operator, is h bar over square root of minus 1 d by d phi. It has a particular simple form for the z operator, right? The x and the y operators are quite a bit more complicated because those include, x and y, include terms that have to do with the azimuthal angle, whereas the z operator only has the angle with respect to the z-axis in it. So let's continue with quantum angular momentum. If we evaluate that operator in spherical coordinates for the square of the angular momentum. So take each of those terms and square them out. Then I've got the overall operator for the square of the angular momentum. And when we plug that in, we find that it's equal to this. And this should look a little bit familiar to you, I hope, in that it actually contains all of the angular terms in the Schrodinger equation. And the angular part of the Schrodinger equation is written out here. Minus h bar squared over 2 times the mass of the particle, 1 over radial distance squared. So there is still a radius in here within the Schrodinger equation. And if you write that out, you find out, compare it to this, that this term here in the Schrodinger equation is angular momentum squared operating on psi over 2mr squared, which is the rotational kinetic energy for a particle in a given state, in that wave function state. And remember that our solution to the actual differential equation last class, at least the statement of the differential equation, gave us the square of the angular momentum magnitude operator operating on psi produced L times L plus 1 h bar squared psi. That is, these are the eigenvalues of this operator operating on the wave function. So the magnitude of the angular momentum is quantized, but it's got some sort of weird numerical value. It's not precisely equal to an integer. It has integer relationships. It can be shown, you can just actually do this yourselves, perhaps I'll make it a homework problem, that the square of the overall magnitude of the operator for the square of the overall magnitude of the angular momentum and the z component of the angular momentum produces a commutator which is 0. And when this is the case, then we know that it's possible to simultaneously find eigenfunctions and eigenvalues for the total angular momentum and for the z component of the angular momentum. So the total angular momentum squared operating on the wave function produces what we just had on the previous page, square root of an integer times integer plus 1 h bar psi. And the z operator operating on the wave function yields the magnetic quantum number, m sub l psi. And mathematically, we had the constraint that m sub l is equal to 0 plus or minus 1 all the way up to plus or minus l. So there will be an odd number of m sub l's starting at L, going down by steps of 1 until you get to minus L. By the way, the Cartesian components of all of the Cartesian components of the angular momentum do not commute. If you actually go through and do the arithmetic on the operators that we have, then it's not too hard to show that the commutator of Lx, Ly is minus IH bar Lz. And similarly for the other two commutators. So those are not 0, which means that you cannot simultaneously measure Lx and Ly to infinite precision. The value of the z component of the angular momentum, we mentioned, is m sub l times h bar, right? And the magnitude and the largest value that the z component can have is equal to that integer, where the largest integer that we can have is going to be L. So the largest value of the component along the z-axis is going to be an integer times h bar. And that's what's demonstrated here. The z component, there's the z-axis, the z component of the angular momentum where the magnitude of the angular momentum for L equals 2 is equal to square root of 2 times 3, L times L plus 1, square root of 6, which is greater than 2. And the projection on the z-axis is going to be these integer steps where the length of the angular momentum vector is not an integer. It's greater than the largest value of m sub L. And you could make a reasonable argument that the reason for that is that the largest value of LZ is smaller than the length of the angular momentum vector is that there will always be uncertainty in Lx and Ly. If Lz is known precisely, Lx and Ly can't be known precisely because of the uncertainty relationship. So, in fact, this vector here actually effectively precesses due to the unknown values of Lx and Ly, and those would be included in the overall magnitude. If the z component were equal to the magnitude of L, then Lx and Ly would have to be 0, which they're not permitted to be by the uncertainty principle. For measurements, angular momentum is important because angular momentum gives rise to a magnetic moment. And again, to discuss that, we make a classical analogy and then make a shift to talking about the system as though it is a quantum system. So let's start out and think about a particle going in an orbit around a point. So this could be an electron going in an orbit of radius r. So charge q, mass m for the particle as it goes, speed v, and radius r. It forms a current loop, therefore. We've got an electron that goes around, and this electron, classically, passes through the same point repeatedly, and we can estimate the current then by asking how frequently it passes through that point. So let's come back to the classical idea. We have the velocity and the radius. So the current is the charge divided by the time that it takes for it to go around a loop once. So if we divide that by that, then we get the average flow of electrons through the system. And that period for oscillation, the repeat time, is 2 pi r over v, the distance around the loop divided by the velocity. What about the magnetic moment? For a current loop, the magnetic moment of the current loop, ignoring vectors for the moment, magnetic moment for the current loop is equal to the current in the loop times the cross-sectional area of that loop. So magnetic moment, the magnitude of the magnetic moment in a particular direction is current times projection of the area onto the plane perpendicular to the direction that we are interested in. So looking at the magnitude, the magnetic moment of a loop like this is equal to, with an electron going around at a certain speed v, is equal to qv over 2 pi r. There's my velocity divided by period. And I need charge, all right? Charge divided by period times the cross-sectional area, pi r squared. Put it all together, magnetic moment is qvr over 2. But we can relate this to angular momentum because we know that L is equal to r cross p, and the magnitude of that is mrv, beginning to look like that, times the direction of the angular momentum. So I just put a unit vector in there. So the magnetic moment for a system in which a charge, q, goes around in a circle with a given angular momentum about that point, about the central point, it ends up, when we make all our substitutions, to be the charge that's moving divided by twice the mass of the charge times the angular momentum. So we've found a magnetic moment from an angular momentum. All of what we've done up to this point is classical. Now, the quantum mechanical trick at the level of this course is simply to recognize that the angular momentum can be written as a quantum mechanical quantity. So how does this affect what we actually observe? Right? If a system with a magnetic moment is placed in a magnetic field, then there will be an interaction energy. The magnetic moment will classically align along the field or anti-parallel to the field. So parallel or anti-parallel to the field. This should be a vector here. And the energy of the interaction will be minus mu dot B. That is, if the magnetic moment is along the magnetic field, then the energy is lower. And that magnitude ends up being minus q over 2m, angular momentum dotted into the magnetic field. So for a field along the z-axis, a term gets headed to the Hamiltonian because this is energy, right? So I'll write that h sub b. And that's equal to the charge times the magnetic field divided by twice the mass of the particle, the electron, for the hydrogen atom, times the z operator in Hamiltonian acting on the wave function is going to produce an energy. So that energy of the eigenfunction, remember the eigenfunction is for the entire state, including the Coulomb interaction, and we want to get an idea of what the effect of the magnetic field is. So we can look at what is the magnitude of the energy associated with this. So the change in energy of a state that has angular momentum and a component along the z-axis, which is equal to m sub L, is equal to charge times the magnetic field divided by twice the mass of the particle times the quantum number, magnetic quantum number, times h bar gives us our shift. Or quantity that we're going to call the Bohr magneton, magnetic field times magnetic quantum number. That Bohr magnitude is equal to about 5.8 times 10 to the minus 5 electron volts per Tesla. It's called the Bohr magneton. Okay? Projects. What we've learned so far is that for any state with a particular L, let's say we put one electron in a particular state, the 2p state, then the number of transitions between the 2p and the 1s state will split out into 3. So for L equals 1, it splits to 3 transitions. So that's what we should see spectroscopically. 3 transitions, 1, 2, 3. Split by something less than 0.03 nanometers, 0.3 of an angstrom. And that was observed for some atomic systems, but not the simplest ones. Zeeman did other measurements, and remember at the time that he did his measurements, there was no theory. He just did very careful spectroscopic measurements after building a spectrometer. So we predict that a magnetic field will split into an odd number of shifted lines. Zeeman, for simplest molecules with one electron in the valence, observed this. In the absence of a magnetic field, the sodium D lines, so those are in the yellow if I remember correctly, the sodium D lines are just single lines in the spectrum. When it is inspected more carefully in a magnetic field, we see that one of the D lines splits apart into 4 lines, so 1 split into 4, not 5, and there's no line down the middle. We would have expected one down the middle. and the other sodium D line splits into 6. Oh, there's supposed to be 6 there. There should be 6 there. My eye's only seeing 5, but there are 6. There should be 6. I think that this is 1 and it's very weak. So the theory is missing something. The second experiment that tells us that the theory is missing something is the Stern-Gerlach experiment, where our magnetic dipole is put, if our magnetic dipole is put in a diverging field, then the dipole experiences a force in the field, a translation force in the field. So this dipole in this field will move up or it will move down. In this case, it's the dot product between the magnetic field, the gradient of the magnetic field operating on this dipole moment cause it to move down. And in this case, the gradient of the magnetic field operating on this moment causes it to move up. So we expect while the atom is shooting through a divergent magnetic field, that we will see a beam of atoms passing through this field to split into an odd number of lines. So the example is here. By the way, there should be no curvature out here. In this region, there's no magnetic field, so all the curvature occurs inside of the magnet. Then it comes out and goes as in a straight line to the screen upon which it's captured. And they used silver for this experiment because the silver just deposits directly onto a piece of glass, for example. And you can observe where the silver actually arrived. And silver is nice, we know now, because it's got one valence electron. So we would expect that actually for the one valence electron in a 1s state, which isn't the case for silver, we'd expect no shifts. What we actually see are that it splits into 3. And that tells us that something, or rather not what we actually see, what we would see if there were a magnetic moment here, is that the incoming beam would split into 3. That's the prediction. What's actually observed is that the incoming beam splits into 2. And this is not a very uniform field, so the splitting is sort of unequal. However, right at the center, we can see that this single line here is split into 2. And this is inconsistent with our magnetic moment for angular momentum that we have just talked about. So either we've completely got it wrong or there's something else going on. And as you can see in the label on the top of this slide, the Stern-Gerlach experiment establishes that electrons have spin and that it can't be integer spin, because if it were integer, quantization rules would tell us that the electron will split, if it were integer, will split into an odd number of lines. We don't. We only see 2. So here's the conclusion. Electrons have a magnetic moment. That magnetic moment in a magnetic field can only assume 2 orientations, parallel to the field or anti-parallel to the field. So we're going to create a new quantum number, m sub s, where the number of allowed values for m sub s is equal to the magnitude of the spin times 2 plus 1. So if m sub s, if m sub s were half integer, that would be the magnitude of our spin. 2 times 1/2 plus 1 would give us 2 lines. M sub s has got to be two-valued because of this Guerlain experiment. And it doesn't have that mu equals 0 line, the one that we expect for the zero projection of an integer. So it was proposed that the quantum number s is equal to 1/2, and that m sub s for the electron, a single electron, is minus 1/2 or plus 1/2. And then the two independent indices, m sub l and m sub s, are put together to specify the states according to the z component of L and S. Experimentally, it is found that the electron spin magnetic moment, we can find that by comparing it to the actual splitting of the beam of atoms as it passes through a divergent magnetic field, yields magnetic moment mu sub s for spin equal to minus charge on the electron divided by the mass of the electron times the magnitude of the vector that describes the spin. Note here that this equation is different from the magnetic moment for an electron in an orbit. There, the magnetic moment was E over 2m, Q over 2m, times the magnitude of the angular momentum. So electrons don't quite behave like a simple object with angular momentum. Relationship between spin and magnetic moment is different than angular momentum would be. So in talking about the spectra, now again, experimentally talking about spectra, there's a language that is used that is common in chemistry and in physics and other spectroscopic measurements that is associated with the quantum numbers, but its origin comes from a time before quantum numbers were known. So we can describe electronic states by listing the quantum numbers: principal quantum number n, angular momentum quantum number, angular momentum projection, and spin projection, plus or minus 1/2, steps starting from plus L down to minus L is steps of 1, and the angular momentum. So m sub L and m sub s is a projection of either the angular momentum or the spin, whatever, a spin vector, on the z-axis. And m sub L has got these rules. It's got to be less than L times L plus 1 square root, and m sub s is plus or minus 1/2. The levels, remember the primary spectra of hydrogen are described by transitions between levels that correspond to 1 over n1 squared minus 1 over n2 squared, initial versus final state. So we just leave the principal quantum number to be what it is. N is equal to 1, 2, 3, 4, for example. The angular momentum quantum number is now specified as S for angular momentum 0, P for angular momentum 1, D for angular momentum 2, F, and G for higher orders 3 and 4. Those are had their origin in observations of spectral lines. So S stands for sharp, and normally it's a bright line. P stands for principal, D for diffuse, F for fundamental. Those are just words. And then G and H, they didn't actually come up with words to describe this. They just said, well, there are others. And so I wrote a joke here. It is from the Sound of Music. So when talking about angular momentum of a system, it turns out to be useful sometimes to speak in terms of the total angular momentum, J, where J is the vector sum of the orbital and electron angular momentum. So this is regular angular momentum. This is spin. J is equal to L plus S. And the total angular momentum is conserved in all interactions, but not necessarily L or S individually. So that's why we need a J, because that is conserved in all transitions. The total angular momentum has the value magnitude of J is equal to square root of an integer times an integer, half integer, depending upon the number of electrons in the system. One electron, then it's going to be half integer. J times J plus 1 H bar, where the possible values for J run from L, absolute value of L minus S, up to the absolute value of L plus S. Actually, it's minus the absolute value. In spectroscopic notation, we label the value of the total angular momentum, J, with a subscript. We label it, we tell you what state an electron is in by giving it the subscript that describes J. And then that follows the letter code for orbital angular momentum. So, putting all our quantum numbers together, the notion 3p3 halves denotes a single electron in the system, be capital P if it were many electrons being put together. Single electron in the system that's in the n equals 3, L equals 1, denoted by P, and 3 halves, which tells us that L is being added to S. L is 1, S 1 half, 3 halves. That denotes single electron in that particular state. That spectroscopic notation can be used to describe state of an atom with more than one electron. And that is usually written by a convention as a capital letter. So the notation 3, capital P, 1 half, denotes a sodium atom. Well, can denote a sodium atom. It's an electron. It's a system in which the total angular momentum is 1, hence P, and it's in a spin 1 half state, so there's got to be an odd number of electrons in the system. So that could denote a sodium atom with its electron in the n equals 3, L equals 1, J is equal to 1 half state. So that would be L minus 1 half. In the filled shells, the electrons are always paired off in such a way that the total angular momentum and the spin are 0. Here's an example. Total angular momentum and its Z component for an electron in the ground state of hydrogen. So the ground state can only have a value for angular momentum of 0. So it's the 1s state. And but there's still an electron, so the spin is 1 half. So J can have the value J is equal to Ls plus 1, L plus 1. So 0 plus the spin is 0 plus 1 half. That's 1 half. All right. And if that's the case, then M sub J can be plus or minus 1 half. And the total angular momentum is, again, magnitude is equal to square root of J times J plus 1 H bar, which for this state, because J is 1 half, is square root of 3 over 2 H bar. And this state is called the 1s 1 half state. I'll save this for actual class. We'll go over it. Okay, so what are some of the other consequences of angular momentum and spin? That spin of the electron can give rise to further energy splitting of lines due to the magnetic field induced by the angular momentum of the proton around the electron. So if, once again, I think classically of my electron as just going around, that current actually forms a magnetic field, which, actually, let me take that back. So I have an electron in a given state, and it's going around the origin with angular momentum L. Now what we're going to do is think of the electron as being the fixed quantity and the proton as circulating the electron. If that's so, the circulating proton gives rise to a magnetic field which interacts with the spin of the electron in order to produce an energy shift there as well. So the magnetic field due to the orbiting proton, and remember, in the electron's frame, it sees an orbiting proton. In the proton's frame, it sees an orbiting electron. And in both cases, that gives rise to a magnetic field at, in the first case, the electron, and in the second case, it is the proton, magnetic field of the proton. So there's our field. And once again, making the analogy, the classical analogy to momentum, we find that the energy shift is somewhat smaller than the energy shift for a 1 Tesla field. The energy shift is about 10 to the minus 5 electron volts. Remember that we had about 5.8 before for 1 Tesla field. Right, so these shifts due to the electron seeing a magnetic field from the circulating proton looks like this. It's got an extra factor of alpha to the fourth in it, where alpha is called the fine structure constant. And this shift due to the magnetic field due to the proton circulating about the electron is actually observable in the energy of the electron.